Hello, my name is Sonika Kurode, and this is my lab report for the Oscillations Lab. So the tracker model that we are using is the provided video of an oscillating spring, and tracker allows us to analyze the real-life scenario. And our computational model is a model created using values from the video and different formulas. So the purpose of the lab today is to see if the model adheres to the energy principle, and we're going to be comparing the observed model to the predicted computational model to analyze motion and energy. The computational model allows us to see the ideal scenario with the exact equations that we enter. So the fundamental physics principles that we're using are Newton's second law, which we are using the derived update formulas to see the change in position and velocity over time, and the energy principle, which is basically that if there's no external force on the system, the energy is conserved within the system, meaning the total energy change would be zero. And a quick overview of the result is that the system consistently had a total energy change of zero, which adheres to the energy principle. Here are the different equations that we're using. We're using the different energy equations for kinetic, gravitational, and spring, the different force equations for spring, gravity, the update formulas, and formulas to find the spring constant and the original spring length. I also used the graph from tracker to find the period of oscillation, as you can see in the picture to the right. So the model, the system is mass, spring, and the earth, and the surroundings are nothing. The initial conditions, I found that the K factor is 6.862, the original length is 0.126, the mass is 0.402, and the mass's initial velocity is shown over there, and the initial position is shown too. So the initial velocity was zero. So in the video, the spring is released and swung in an elliptical shape so that it moves in both the X and Y directions. And you can see on the picture to the right, all the points that I plotted and the graphs that came out from the X and Y axis through tracker. So here is the code that I wrote. The first section includes the equations to create the vector for the length of the spring. The next section, I added the equations from the previous slide for kinetic, gravity, spring, and total energies. In the next section, I inputted the force equations for gravity, spring, and total force. Next are the velocity and position update formulas. And the final section calculates the energy change using the final energy minus the initial energy for each type of energy, including total energy. Here are the results I got from the computational model. You can see the energy graph for kinetic, gravitational, spring, and total energies in the image on the left side. And on the graphs to the right, you can see that the model and the experimental graphs are more or less the same. You can see that the experimental graph is not completely perfect, whereas the model is completely perfect because the computational model is the ideal scenario, whereas in real life there are always some discrepancies. So some sources of error from the video and the tracker values is that since I created the tracker model using points that I clicked on the video, it could have some human error. And there could also be motion on the z-axis that isn't accounted for in the models. So for the what does it mean question, since there are no external forces, the energy change should be zero. And you can see on the orange line, it's consistently remaining at zero, which means that the energy within the system is conserved. I also calculated the oscillation period using the time values in both the X and Y graphs on tracker, and you can see the difference in oscillation periods that I got. And even though I found different values, this would only affect the spring constant and the original length, which would affect specific values within the energies, but the total energy would still remain zero since energy is conserved, no matter what position you use. Thank you so much for listening. Bye.